Now, whenever you have a product of spin operators, you know that the sum is relevant because of the simple identity. If you form the sum of these two things, these two operators, and call that S, you would have that SE dot SP is 1/2 of S total squared minus SE squared minus SP squared. Now, if you want, you could write everything in the language of tensor products. That would be the right way to write it, but it's a little cumbersome, and you don't get in trouble by writing this. It's not that subtle. Here it would be the product of these things would be something like SE I tensor SP I sum over I. That's really what it means, the product of these operators. And you know the total spin operator, what it means. It's tensor products of sums. And anyway, you can check that in that language. Is probably a good idea. But we can be naive. Now, the SE squareds and the SP squareds, these are spin 1/2 things. So you know what the eigenvalues of these things are. They are the same because both are spin 1/2. So this is 1/2 S squared minus H squared, 1/2 times 3/2. So it's 3/4 minus H squared times 3/4. And there's two of them times 2. So it's 1/2 S squared minus 3/2 H squared. So we can write SE dot SP as 1/2 H squared S squared over H squared minus 3/2. So that's our operator. And now, here comes the issue, and here is the addition of angular momentum. We have this basis. On this basis, we cannot evaluate the Hamiltonian and get anything meaningful. We have to find the states that are diagonal for this Hamiltonian. Now, this Hamiltonian is really a number times this product, and the product is the total angular momentum operator up to a number. So the states of the total angular momentum are the states for which this operator is diagonal. So instead of looking at these states, these 4 states, we should look at the triplet that we found before and the singlet. So if I want to evaluate this object, I now have to simply look at the triplet and at the doublet. So what is this for the triplet and for the doublet? 1/2 H squared. If I'm looking at the triplet at S equals 1, you would have here 1 times 2 times H squared, so it's just 2 minus 3/2. And if I'm looking at the singlet, these are 3 states and 1 state, have 0, so minus 3/2. So this is 1/2 times H squared is, I can put here H squared times minus 1/4. I put the 1/2 in. And here minus, plus 1/4 and minus 3/4 here. This is for S equals 1 and for S equals 0. So this is what this operator does on the basis that it's diagonal. On the 3 states of the triplet, it gives value 1/4 H squared. On the single state of this singlet, it will give value minus 3/4. So in a sense, we've really solved this now, because this is what this operator gives you on those states, and therefore on the expectation value of this operator on the triplet is just 1/4 h squared, and on the singlet is -3/4, and therefore those are the energy shifts that you have here. So I can write this whole delta H, and I will write it as delta E times SE SP over H squared. That will be my rewriting of this whole thing. I'll put an H squared down here and an H squared there, and I'll call this delta E. And why am I allowed to call this delta E, or what does delta E mean? Delta E here means the split between the triplet and the singlet. Because when you evaluate this thing for the triplet, it gives you 1/4. When you evaluate this for the singlet, it gives you -3/4. So the 4 states, for the triplet, it gives you 1/4. So 1/4 delta E. 1/4 delta E in that notation. And for the singlet, gives you -3/4 delta E. So it's down here, 1 state only, and here is -3/4 delta E. So the whole split here is delta E. So this is what's happening to the levels of the ground state. These 4 states now with this perturbation reorganize themselves nicely into a triplet that goes up in energy and a singlet that goes down in energy. And this is the hyperfine splitting. So the delta H, the expectation value on the triplet, gives you the 1/4 delta E. The expectation value on the singlet gives you the -3/4 delta E. By the theorem of perturbation theory, those are the shifts of those energy levels. So what remains to see and enjoy here is the values of these numbers. What are they? Because there's a lot of physics associated with these numbers, things that it's good to get familiarized. So we had this here. So this delta E is GP mu 0 E squared over 3 pi ME MP H squared over A0 cubed. This is the SI units are not the most fun thing in the world. You have to look what A0 is, and you can do a little operation here and get rid of the mu 0 with a C and things like that. So manipulation of this constant. Let me give you the basic relation. A0 in SI units, it's impossible to remember it. I never use those units. MEC E squared. So you also have to remember that mu 0 epsilon 0 is 1 over C squared. And with those two, you will be able to show that this becomes 4 GP h to the 4th over 3 MP ME squared C squared 1 over A0 to the 4th. So a little work that I'm leaving for you in checking that these two relations allow you to write it this way. Now, there is the fine structure constant of electron. This formula, I would say, is ununderstandable, the way it's written like that. No intuition whatsoever. You have to write it in a different way if you want to understand something from it. It would be a mistake to start plugging numbers at this stage. So what should you look for? Well, this is SI units. But now, actually, here, you don't have the SI units or anything like that. You can use whatever units you want. And there's the so-called fine structure constant, alpha, which in Gaussian units is E squared over hc. And this quantity is 1 over 137. And it quantifies the strength of electromagnetism, and it's worth trying to write things in terms of this. Of course, you need to know what A0 is, and you can look it up in Gaussian units. In Gaussian units, A0, this is SI. In Gaussian units, it's just whatever you have here, h squared over m(e) squared. Only that. So this whole thing, this is GP here, this whole thing can be written in a more understandable way. I'll write for you the answer. Again, something you should do. 4/3 GP ME over MP alpha to the 4th MEC squared. This is a formula I claim a human can understand. Why is that? First, I see the units already. This has units of energy, and we're looking for energy. This has no units, this ratio of mass has no units, and this constant have no units. So units are manifest. And this is a nice unit of energy. This is the rest mass of the electron. Times the c squared, rest energy of the electron. And alpha is a conceptual thing, the fine structure constant. It's 1 over 137, it's small. So things that you may remember that allow you to understand the smallness of this hyperfine splitting are the following. That here is the rest energy MEC squared, is the rest energy of the electron. If you multiply it by an alpha squared, that's roughly the Bohr energy. Those 13.6 EVs up to a factor of 2 is alpha squared times this. And that also should give you some pleasure to see that formula. Because you see, well, the Bohr energy, where does this all begin? Well, you have energies in this problem, so the Bohr energy must be related to the canonical energies. And the canonical energy is the rest energy of the electron. And here it is. This is all affected by the strength of electromagnetism. It's affected by an alpha squared. So the rest energy of an electron is 500,000 EVs. By the time you multiply by alpha squared, which is about 1 over 20,000, you're down to those 13 or so EVs, up to a factor of 2. So this is the Bohr energy. If you multiply by another alpha squared, this is the fine structure modification of the energy level. So LS splitting, spin orbit coupling. Let me write it like that, spin orbit. So spin orbit coupling is another factor of alpha squared smaller than the Bohr energy. So rest mass of the electron, alpha squared, to diminish it 20,000 times, you get the Bohr energy. 20,000 times smaller is the spin orbit coupling. And here you have basically this alpha to the 4th, so this would be comparable to spin orbit. And you have a further reduction, mass of the electron over mass of the proton, which is like 1 over 2,000. More precisely, 1 over 1836. So now you can plug numbers. In fact, it's kind of easy. You can Google the mass ratio of these two particles. You know the GP. And the answer is delta E equals like a millionth of an eV. So the value that I have here recorded is 588 times 10 to the minus 6 eV. A very small energy shift. So we have that, but we're not done with the numbers. Let's have a little more fun with these numbers and calculate the wavelength of a photon that would be emitted by a transition between those two levels. So the energy difference between the triplet and the singlet is this. So if you have an interstellar hydrogen, even a microwave background photon might be enough, will be enough to excite this ground state from the singlet to the triplet. And then it will stay in the triplet, and at some moment it will decay. And you want to know what is the wavelength of that photon that is emitted. So for that, we have that the wavelength is c over the frequency. Frequency times wavelength is the speed of this object. And c over, now you would have delta E over h, not h bar. We're talking normal frequency, not angular frequency. This h is 2 pi h bar, so here we would have 2 pi h bar c over the delta E. This is something you can calculate, even without a calculator. 2 pi, leave it there. H bar c is known to be about 198. Yeah, 97 is probably more accurate. MeV times Fermi. And here below you have this 5.88 times 10 to the minus 6 eV. So what is this? 2 pi over 5.88 times 197 times 10 to the 6 eV, that's MeV, and let's talk centimeters. A Fermi is 10 to the minus 13 centimeters. People remember it maybe like 10 to the minus 15 meters. And here you have just 10 to the minus 6 eV. So the answer will be in centimeters. And if you do this, this will be 10 to the 12, 10 to the minus 1 times 19.7. So it would be 19.7, 2 pi over 588 times 19.7 centimeters. So this is a little bigger than 1, so it should be about 20 centimeters. The exact answer is 21.1 centimeters, and that's the famous hyperfine splitting line. It was first observed in 1951 by Ewan and Purcell. Purcell is the person that wrote this lovely electromagnetism undergraduate book. This corresponds to a wave, to a frequency of 1420 megahertz. And now you can ask, all right, so this is the line we should see. What is the lifetime of this excited state? How often does it decay? Now, the lifetime is astonishingly long. The probability for this decay from the upper level to the low level is highly suppressed. Would be an interesting calculation to do, probably a graduate level quantum mechanics calculation. And the result is that the lifetime of this state is extremely long. So how long? 1/3 times 10 to the 15 seconds lifetime. 1/3 times 10, 1/3 times 10 to the 15 seconds. If you want to quantify this, there's also an easy way to do this, because 1 year, by these accidents of nature, is about pi times 10 to the 7 seconds. It's really funny. There's no reason why pi should be there, and it just happens to be fairly accurate. I think this is good to even about 1%. So if you want to divide by years, you divide by pi times 10 to the 7, this thing, and that gives you that the lifetime of the excited state is about 10 to the 7 years. Lifetime. Time. It's about 10 to the 7 years. So that's 10 million years. You have to wait for 10 million years to see one hydrogen decay. Happily, in interstellar media where this is studied, there's a lot more than one of them, so it happens fairly often. And this signal is particularly useful to do all kinds of measurements in interstellar media. It's been used to measure rotational speed of galaxies through the Doppler shift of this line. And given that extraordinarily long lifetime, if you remember the uncertainty principle, delta E, delta T goes around h, very, very long lifetime implies this is a line that is very accurate, very sharp, extraordinarily sharp, with millions of years of a lifetime. So this is not a broad line that you would have problems seeing its Doppler shift. This is an extremely clear signal. So this is the hyperfine splitting. It's a simple application of the addition of angular momentum of spin 1/2 particles, and it's also an extraordinarily useful physical phenomenon.